Hey guys, welcome back to your next lecture video. This one should get you through that last page of notes that I handed out in class today. Hello? There we go. All right, homogeneous means uniform. Their substances are blended consistently throughout. There are two types of homogeneous mixtures. We got alloys and solutions. Now, alloys are the combination of two or more metals made by humans because they have properties superior to pure metals. Now, I should say that the properties are kind of what we want them to be a little bit. Sometimes pure metals have properties that are better than alloys, and in those cases we use the pure metal. But a lot of times an alloy will have different properties that make it applicable to different uses. And then as you can see here, it's not always two or more metals. Sometimes there's a non-metal in there, like in steel. Carbon is a non-metal mixed in with iron, but it's just a mixture of metals and other elements in order to gain the properties that we find desirable into those materials. I believe second and sixth period was able to watch this video, or maybe just second period, but tomorrow I'll make sure we get that up in class for those who didn't watch it today. So continuing that, we got solutions. Now solutions, I'd like you to know a little bit more about them. So we have some more definitions here. A solution is made by dissolving a solute into a solvent. You got an example? Sweet tea, the entire solution, is made by dissolving tea, the solute, and sugar, another solute, into water, the solvent. So solvents are always the major part of the solution. Like water is the main part of sweet tea, and it's almost always a liquid. Solutes are the minor part of solution and can be a solid, liquid, or gas. In the first example I gave you, sweet tea and sugar are solids dissolved in water, a liquid. Here's an example, carbonated drinks, you got CO2, a gas dissolved in water, and then rubbing alcohol, C3H8O, is a liquid that is dissolved in water. Now, for these three terms, solutions, solvents, and solutes, those words are very similar to each other. So if you're just now learning them, I know for me, my brain would probably get some of them backwards. And so here's a little way to help you keep track of it, especially these two right here, solutes versus solvents. So solutes is the minor part of solution, or the less part, whereas solvents the major or the more. And the way I keep that straight is if you look at the words solute and solvents, solute has one less letter in it than solvent. So solute is literally a smaller word and it means the minor part of the solution, whereas solvent is a bigger word and it means the major part. So it's like the size of the word goes with the meaning really nicely. And then the entire thing, the solution, well, solution actually has the most letters out of all of these. So kind of the size of the word goes with kind of the size factor of what we're talking about there. Solute, the minor, the smallest word, solvent, the major, the bigger word, and solution, the biggest word, and it's the combination of all. And then heterogeneous mixtures, non-uniform, substances not blended consistently. So most rocks and other things in nature fall into this category, like a piece of granite. If you look at it, you can see the components. And if you took one chunk of granite and compared it to another chunk of granite, they might have similar stuff, but they would not be mixed evenly in exactly the same way. And so I have this thought question here. I believe in second period we got to this point where we actually answered this, but I'll leave this hanging here for sixth and seventh period to think about, and we'll talk about this in class tomorrow. Why do you think most natural things are heterogeneous mixtures? Go ahead and give us some thought to that and see if you can come up with an answer. Please don't shortcut this and Google it. Like, you could find some answers. I actually just want to see what you think and what you could come up with here. So even if you get it wrong, you're not going to lose any point or anything for it. So please actually just try if you're going to try and don't just look it up. Okay, moving on to section 2. So section 2, we're going to talk about the atom, composition of the atom. So the atom is a very important piece of matter. It is the smallest unit of matter that has the chemical properties of its element. And so it is the smallest unit that still has properties of that element. When we talk about a lot of things in this class, like I told you on day one, I'm going to use human analogies. And so if we're thinking about elements, for example, let me see if I can switch over here to periodic table. Okay, you got all of these elements here, and they all have something that makes them unique than the rest of the elements. And that kind of is like you as a person. You are unique. And so I want to just throw out there, elements are kind of like individual people. And so if atoms are the smallest part of an element that still has its properties, I want you to kind of think, what's the smallest part of a person that still has, or I guess any living thing that still has the uniqueness of that thing in it. It's just an analogy here. I just want to see if you can kind of like connect the dots. What's the smallest unit of a living thing that still has all the pieces that are unique to that thing? Just think about it. See if you can come up with an answer as you come back to class. So atom, that term comes from the Greek word atomos, which means uncuttable. Today we know that atoms are in fact cuttable, quote unquote there, and that there are particles within them. Atoms themselves are composed of smaller things called subatomic particles. And those subatomic particles are protons, neutrons, and electrons. Those are the words we gave to name those pieces. Every atom of every element is composed of these particles, which is kind of crazy when you think about that periodic table just showed up there. 118 different elements, and all of them are made up of these same three materials. So where does all of the variety come from? What makes atoms of one element different from the atoms of other elements is the ratio of the subatomic particles within each of them. So they're all made up of protons, electrons, and neutrons, and it's just the ratio of those, the amount of those, that makes one element different from another, which gives things their different chemical properties, which gives them different bonding behaviors, would that make different compounds, and all the variety and diversity that we have in life just comes from different ratios of these three building blocks. So what I want you to do is just a little practice at counting up the number of these subatomic particles within an element. So we're going to switch over to that periodic table soon, but let's just start here with this one. Think about this. We have 2 protons, 2 neutrons, 2 electrons. Can we think, what element would this be? Well, if we think back, the number of protons is what connects to the atomic number, which is the identifying number for an element. So if this has 2 protons, then the atomic number for this element would be 2, which would identify it as helium with an atomic number of 2. But the one from our notes here is 87. So which element has 87 pieces? That would be francium, or Fr. Okay? Atoms of Fr contain 87 protons, 87 electrons, and 136 neutrons. What about atoms of Ra? Let's go back and find Ra. Where is it? Radium. Oh, it's right next door. Ra, that has 88 protons. So 88 protons, 88 electrons, and 138 neutrons. And then atoms of Tc, I'll leave this one to you. You can either scrub backwards in the video and look at that periodic table, look up your own, whatever it is, I'll leave it for you to fill in those blanks. So let's continue talking about the subatomic particles here. This is a part of your quiz information to know this chart. So protons, we use the symbol of a lowercase p. If you're not listening to this video, you might miss out on this. That needs to be a lowercase p because if you look back at the periodic table, a capital P is already used for the element phosphorus. So if we're talking about protons and we use that symbol, it's a lowercase p. In the atom, protons are located in the nucleus, right in the center of it. They have an electric charge of a +1 charge, and they have a mass unit of 1. Neutrons, lowercase n, also existing in the nucleus. We call them neutrons because they are electrically neutral. They have a 0 charge, and they have the same mass as a proton. If you're kind of thinking, one what? Like 1 gram, 1 pound? No, this is what we call atomic mass units, and it's a scale made up to talk about the size of elements relative to each other. And so what we're saying here is like this is the smallest size unit for subatomic particles and atoms. So what we're saying here is protons and neutrons are the smallest piece of matter, and they have the same size as each other. And then electrons, they have the symbol of an E with a little negative sign up there, and they live in the space surrounding the nucleus. They have an electric charge equal but opposite that of a proton, so a -1, equal in electric size and like charge, but opposite. And then they have a mass much, much smaller than protons and electrons, about 1 in 2,000th the size. So the number of protons in the nucleus defines the different type, defines the element type of an atom. It's those protons that define it. And the number of protons in the nucleus is also called an element's atomic number. This is kind of repeated information from the last page of notes, but it's really, really important that this kind of starts sinking in. And then opposite electric charges. You learn about this stuff when we think about magnets, and we learn about those in maybe physical science or earlier years, but opposites attract, and that's true for magnets. It's also true for electric charges. Opposite electric charges attract each other. And so therefore, the positively charged protons will attract negatively charged electrons, and they will attract 1 to 1. So for every 1 proton in an atom, there is 1 electron attracted by it and held to the atom as well. So when we look back at these couple questions here, these 3 questions at the bottom, notice how the number of protons and the number of electrons are always the same there, because these opposites attract each other on a 1-to-1 ratio. And that is where we will leave off on this video.